This time, we are going to prove sets of limit theorems. Specifically for this video, we are going to prove that the limit of the sum of two convergent sequences a sub n and b sub n is equal to the sum of their individual limits L sub 1 and L sub 2. So we have this statement: let a sub n and b sub n be convergent sequences of real numbers with the limit of the sequence a sub n is equal to L sub 1 and the limit of the sequence b sub n is equal to L sub 2, then the limit of their sum is equal to the sum of their individual limits. We are going to use here the definition to prove this, to verify further that this is true. The main parts of the proof will have to first, we're going to express the given limit expression in terms of known limits, because we have here the given limits for each individual sequences. We're going to look at possibility of expressing the entire expression into individual limits. And then we might need the process involving triangle inequalities later on that will help us bound these terms to ensure that specific n is identified so that we will come up with our epsilon. We're talking about epsilon because part of the definition is to let an epsilon greater than 0. So we'll have this part of the proof. We start with letting epsilon be greater than 0, however small is that. We must show that there exists an integer n, or an integer n here, such that if n is greater than n, then using the definition for the limit of sequence and whether it converges to that said limit, the absolute value of the identified sequence, in this case the sum of two sequences minus their limits, that's 1, is less than that said epsilon. This is the goal of this proof. We must show that this is true. So part of that is, again, we're going to express the given into known limits. We can structure it this form. Note that we can simplify the absolute value notation: a sub n plus b sub n minus the quantity L sub 1 plus L sub 2. Of course, this could be removing the grouping symbols. You have a sub n plus b sub n minus L sub 1 minus L sub 2, which could also be transformed into a sub n minus L sub 1. We are pairing this because we are given here that the limit of a sub n is L sub 1, so they must be paired together with b sub n and L sub 2. So as we pair them, this is plus because b sub n is positive, still minus L sub 2. Okay, so we have shown that there are pairings for known limits. We have here again this one and this one here. Then we can use here the idea of a triangle inequality, where if we have the absolute value of the sum, okay, again we have the sum of two known limits, they are under absolute value, this is less than or equal to the sum of the individual absolute values. So you have here the absolute value of a sub n minus L sub 1 plus the absolute value of b sub n minus L sub 2. This is according to the triangle inequality. Since we have established this too, let me change the color to black. Okay, the next part here, once we have expressed the expression into known limits, we can invoke here the individual limits like this and that. Of course, we can construct it like this. Since the limit of the sequence a sub n is equal to L sub 1, there exists, let's say n sub 1, an integer n sub 1, such that if n is greater than or equal to n sub 1, then we can structure using the definition for the limit of sequence: a sub n minus L sub 1 would be less than supposedly e. But since this is just part of the entire triangle inequality here, let us look into how do we bound it properly so that we could express the final result later on to epsilon. Take note that both of them, there are two of them here. Why not express epsilon here as epsilon over 2? So that later on, once we combine them, we will return to the epsilon, the goal of this proof here. Okay? So that's for that. Also, the second, the limit of b sub n equal to L sub 2, then there exists another n sub 2, which is an integer, such that if n is greater than n sub 2, then b sub n minus L sub 2 is also less than epsilon over 2. This is how we make sure that our bounds will be able to, for us to really go back to our epsilon. Okay, that's the term epsilon control. Okay, now after this, since here we're talking about presence or existence of n, not n sub 1 or n sub 2, so we need to make a statement here where there would be a consideration for the n sub 1 and n sub 2 be equal to our n, entire n. So let's say, take n, since we're talking about our n being greater than that, greater than n sub 1, and generally, again, it should be n greater than this. So let's take the maximum. Let's take the maximum of both, so that our n will still be greater than the maximum of any n sub 1 and n sub 2. So maximum of n sub 1 and n sub 2. Okay? After that, we're taking that, let's say if n is now greater than n. Now this comprises of what is the maximum of n sub 1 and n sub 2, meaning this is very large, or large enough. And then when we say n is greater than that, then we have met the standards for our definition. So after this, we can now say that, let's use the triangle inequality here, this, which will lead to that. Okay, so you will have, this is the original form, minus L sub 1 plus L sub 2. This is equal to the absolute value of, again, a sub n. Cutting this one here, I will not be showing this. I'm going to proceed to this part immediately to show later on the triangle inequality, minus L sub 1 plus b sub n minus L sub 2. Okay, so we have here the absolute value of the sum according to triangle inequality. This is less than or equal to the individual absolute values, the sum of the individual absolute values. Okay, now take note that we have shown here, this one here, this portion, okay, that the absolute value of a sub n minus L sub 1 is less than epsilon sub over 2. This is also true here. So this is even further less than epsilon over 2 plus epsilon over 2, which is just equal to epsilon. So looking into that, this statement here and going towards here, we can say that this is the final statement, minus L sub 1 plus L sub 2 is less than epsilon. This one here, taken from this, then we have satisfied the thing that we are trying to show. Okay, so once we reached into that, we have shown that really this statement is true with the limit of the sum of the sequences is equal to the sum of their individual limits. So just simply state here, since epsilon greater than 0 is arbitrary, okay, however small, okay, we conclude that it's now time for us to just show the limit. The limit of the sum of the sequences is equal to L sub 1 plus L sub 2. This is the end of this proof. We have shown here that this limit theorem for the limit of the sum is true for sequences a sub n and b sub n following this proof. Please review this proof as part of your preparation. Thank you very much for watching.